Have you ever stared at a circuit diagram and just felt completely overwhelmed? It looks like a tangled mess of wires and you have no idea where to even start. Well, it turns out there's this really elegant trick for that. It's a way to strategically simplify these complex circuits, and today we're going to break down exactly how it works.
So first things first, to really appreciate this technique, we need a worthy challenge, right? We need a real circuit conundrum to solve.
And here it is. Our challenge for today. We've got a voltage source over on the left, a current source on the right, and a bunch of resistors scattered all over the place. Our mission is to find the current, that little I that flows right through the middle 5-ohm resistor. And yeah, right now, it looks pretty intimidating. Seriously, where do you start? I mean, you could try a standard method like mesh analysis, writing out a bunch of equations for each loop, but that current source really complicates things. There's got to be a smarter, more elegant way to solve this, and thankfully, there is.
And this is where we introduce the hero of our story, a really clever method called source transformation. This isn't about brute force, it's all about working smart.
So here's the deal. The crucial point is that we're not actually changing what the circuit does to the outside world. We're just swapping out one set of components for another that's functionally identical. It's kind of like changing the engine in a car. Under the hood, it might look totally different, but it still drives exactly the same. And this slide, right here, this is the core of the entire trick. A voltage source that's connected in series, in a chain, with a resistor, behaves exactly the same as a current source in parallel with that very same resistor. And the magic that lets us do this? It's good old Ohm's law. V equals I times R. That simple formula is the secret key that lets us convert back and forth.
All right, theory is great and all, but let's get our hands dirty and actually put this into practice. We're going to take our tangled mess of a circuit and tame it, one strategic swap at a time. Okay, let's look at the right side of the circuit. We have a 1 amp current source sitting in parallel with a 10 ohm resistor. This is the perfect setup for our first transformation. Let's swap this pair out for its voltage source equivalent.
And just like that, it's transformed. Using Ohm's law, the voltage is 1 amp times 10 ohms, which gives us 10 volts. The resistor that was in parallel is now in series, and the rest of the circuit has no idea anything even changed. See how that's already starting to clean things up?
Okay, but we're not done yet. We've got two nice, clean branches now, each with a voltage source and a series resistor. This is the perfect chance to flip the trick and go the other way. Let's turn both of them into their current source equivalents.
So we apply Ohm's law to both branches, and our two voltage sources become two parallel current sources. The 10-volt source on the left turns into a 2 amp source. Over on the right, the other 10-volt source becomes a 2/3 amp source. And now, look what just happened. Everything is in parallel.
And because everything is now in parallel, we can start combining things. It's so much easier. The two current sources, since they're pointing the same way, just add together. The parallel resistors can also be combined into one single equivalent resistor. You see, with every single step, this circuit gets simpler and simpler.
All right, one last transformation to seal the deal. We swap our new combined current source and resistor back into a voltage source and a series resistor. And what we're left with is this beautifully simple single-loop circuit that, honestly, anyone can solve.
And there it is. The current I that seems so impossible to find at the beginning is just 8/7 amps. We took a complicated, messy network, and with just a few clever swaps, we boiled it down to basic algebra. That's the real power of this method.
But wait, it gets even better. This trick isn't just for these basic components. It can actually handle much more complex situations.
So far, we've only dealt with independent sources. The ones represented by circles. Their value is fixed. But some circuits have what are called dependent sources, shown as diamonds. Their value actually changes based on some other voltage or current somewhere else in the circuit.
So what's the great news? The exact same transformation rules apply. It doesn't matter that it's a diamond instead of a circle. You treat that dependent source just like any other, even though its value is a variable. The process of swapping between the voltage and current forms is identical. It's awesome.
And it gets even more powerful. Are you thinking about AC circuits, with tricky components like inductors and capacitors? Well, source transformation has you covered there too. The only real difference is that instead of resistance, you're just working with impedance. But the core principle? It's exactly the same. And you can see here, the principle holds perfectly. A current source in parallel with an impedance can be swapped for a voltage source in series with that very same impedance. It just goes to show you how incredibly versatile this technique really is.
So, what's the big takeaway here? We've basically just added a genuine analytical superpower to your toolkit.
So why does this matter so much? Well, because source transformation lets you take these really gnarly, complex networks and boil them down into simple circuits. It makes analyzing them with basic rules like Kirchhoff's laws way, way easier. And like we saw, its power stretches across DC, AC, and even those tricky circuits with dependent sources. That makes it an absolutely indispensable tool.
You know, the source material puts it perfectly. Sure, you could always use software or just brute force your way through a problem, but real analysis, true understanding, is based on these fundamental rules and theorems. Learning a tool like source transformation, that's the very essence of working smart, not just hard. It's about seeing that elegant solution hiding inside the complex problem.
So, the next time you're faced with a circuit that looks impossible, remember you have a new trick up your sleeve. The only question left is, what complex problem are you going to simplify first?